Welcome, everyone. For today's prep, we're going to be introducing the natural exponential function. And this is probably the spookiest of the functions we're going to be looking at in this course. And let's start with what we've been doing lately, and that is we've been looking at exponential functions. So this is where we have a base term b, which is a constant, and it's raised to the power x. And one special property of these exponential functions is they all go through this point 0, 1. So graphed a few of these different ones here. We have the 1.2 raised to the x. So that's this one right here. We have 2 raised to the x, 3 raised to the x, and 5 raised to the x. So just a whole bunch of different exponential functions. And because they all go through that same point, 0, 1, kind of a natural question then is, what is the slope at x equals 0? What is the slope at that point for all these different exponential functions? And we know how to calculate the slope of a curve at a point. So if we were looking at this point, and let's say we were looking at the exponential function 5 raised to the x, we would plot the point and then draw the tangent line, and then find the slope of that tangent line. And if we did it for 5 raised to the x, we'd see that the slope is about 1.6. And if we did that for 3 raised to the x, we'd see that the slope is about 1.1. And for 2 raised to the x, we would see that the slope is about 0.7. And for 1.2, the slope is about 0.18. So what we notice, if we kind of look for patterns here, as the base value gets closer to 1, the slope approaches 0. But more importantly, if we look, something special happens between these two exponential functions. So between 2 to the x and 3 to the x. And what happens there is the slope goes from being above 1 to the slope being below 1. So we're a little bit above a slope of 1 for 3 to the x, and then we're a little bit below a slope of 1 for 2 to the x. And so a natural question is there a constant that's kind of sits in the middle, in between 2 and 3, that gives us an exponential function that has a slope exactly equal to 1? And the answer is yes. And that special function, or that special number, is e. So there's this special number which we call e, and that gives us a special exponential function, and a property of this exponential function is that it has a slope of exactly equal to 1. At x equals 0. And so this is e to the x. This is our natural exponential function. So this is our big definition here. And even though this is kind of mysterious, it's e to the x, e is just a number. So it's a decimal. It never repeats. And it's approximately equal to the number 2.71. Now, this decimal keeps on going, never repeats. So we can't write this as a fraction or anything like that. It's kind of like the number pi. So we know the pi is a special number, about 3.14. Think of e the same way. E is just a number. It's a special number, and it's approximately equal to 2.71. And one of the things that makes this number so special is that when we form the an exponential function from it, we have a slope exactly equal to 1 at x equals 0. And it's this property that makes this function so nice for calculus. So the first result here, and why we're going to be using primarily this exponential function, is that the derivative of this special function is equal to itself. So the derivative of e to the x is equal to e to the x. And we can prove this using our limit definition of derivative. So we're actually going to prove this. So let's calculate f prime, the derivative, and we're going to use that limit definition. So this is where we did the limit as h goes to 0 of f of x plus h minus f of x all over h. And for this, we're saying f of x is our special e to the x function. All right, so for these ones, good kind of review here. Let's start with f of x plus h. So we're going to plug parentheses x plus h in to this function. And we keep writing our limit sign. And then f of x is just the function itself, so e to the x all over h. And we have some exponential properties that we've looked at, exponential laws, that allow us to rewrite terms when we have addition in the exponent. So we can rewrite that e to the x plus h. We can break that apart and write that as e to the x times e to the h. And now if we look in the numerator, we have 2 copies of e to the x we can factor out. So we end up with the limit as h goes to 0, e to the x times e to the h minus 1 all over h. So I've just factored out that e to the x. And this e to the h minus 1 over h, with this limit as h goes to 0, this is just the slope of the tangent line at x equals 0. So that's what gives us the slope at x equals 0. And we know the slope of e to the x at x equals 0 is 1. So we end up with 1 times e to the x here. Which is just e to the x. So the limit as h goes to 0 of this e to the h minus 1 over h, that's just telling us, those two things together are telling us what the slope of our curve is. And we know what our slope is at x equals 0. It's equal to 1. So this e to the x function is special. So before we go on and do derivatives with it, I want to introduce some, or just practice rewriting, working with this special exponential function. So we looked at it last time. We had this list of all these different exponent laws, and we kind of wrote them down generally for b raised to the power x. All of these are still going to apply for this special number e. So we're going to be able to use all these same exponent laws. So let's try out a little practicing here. So let's look at example 1. And we're going to rewrite each of these kind of more complicated expressions in the form a times e to the kx. So a and k are going to be constants. And when we get to some applications of exponential functions, this is a format that we're going to be looking at quite a bit. All right, so let's look at the first one. We have this expression, 3e to the 2x squared times e to the x, all divided by e to the negative 2x. All right, so let's start with, we want to simplify this down to just a single exponential term. So let's start with the, let's start with the parentheses here. And let's square that. So we have a distribution law when we have multiplication, like we do here, we have a constant, and then we have the exponential term, and we're multiplying them, and that entire thing is getting raised to an exponent, we can distribute that exponent. And that is property 5 on our list there. So if we go back, we're going to do this. We're going to use this property. And we're kind of going this direction. So we have something inside parentheses, all getting raised to a power, and we can distribute that exponent. So let's try it out. So we're going to distribute. So we'll get 3 squared times e to the 2x squared. So we distributed that square term to each of the terms inside the parentheses. So the 3 got its a squared, and then e to the 2x. And if we remember, that distribution only works for multiplication and division. Okay, so now let's simplify this. So when we have a term getting raised to a power, and then that whole thing getting raised to a power, so when we have multiple exponents, the way we simplify this is we just multiply the exponents. And this was property 4 on our list there. So we multiply exponents. And in this case, when we do that, we have our 9. So we can calculate 3 squared. It's just 9. And then if we multiply, we have e to the 4x. And then we have e to the x all over e to the negative 2x. Okay. So next, we can multiply these two exponential terms together. And when we do that, we add the exponents. So we're going to have 9e to the 5x. So we add the exponents. And that gives us the e to the 5x there. And then finally, we have a fraction and we have an exponential term, same base, different exponents. So when we're dividing, we can instead subtract the exponents. So if we do that, we get e raised to the, or 9 times e. And if we subtract these exponents, we're going to end up with a double negative. So we get 5x minus negative 2x, and that simplifies to just 7x. So here we subtract the exponents. And so if we're looking, if we wanted to figure out what is the a value and what is the k value for this, our simplified version here, well, it helps to just write what do we, just to kind of compare, we wanted it in the form a times e to the kx. And then you just kind of match things up. So in this case, we see that the a value is 9, and then the k value is 7. And we're going to see that these numbers have some significance in terms of applications. So it's going to be helpful if we have an expression like this to figure out what those values are. All right, let's try one more, just to get a little more practice. So here we have the square root of e to the x divided by e to the 7x. So first thing, we have division under the square root there. So we can simplify that by same process we did with this. We subtracted the exponents. So we end up with square root, and if we subtract, we get x minus 7x. And if we do the subtraction, we get square root e raised to the negative 6x. And then let's rewrite that root function. So we'll have e raised to the negative 6x, and then that whole thing is getting raised to the power 1/2. And that's because the square root, we're just rewriting that as raised to the power 1/2. And e to the negative 6x was everything inside of it, so that's inside the parentheses here. And now we're in a common situation where we have a base term getting raised to an exponent, and then that whole thing getting raised to another exponent. And the way we simplify this, kind of like what we did before, we multiply those exponents together. So in this case, we end up with e raised to the negative 3x. So negative 6 times 1/2 is just negative 3. And again, it's helpful so we just want to be able to identify what these values are for this term. So if we kind of compare, we wanted it in the form a e to the kx, and we just kind of match things up. So the a term is the number in front of the e, and even though there's nothing visible, there's always something there. There's a hidden 1. So that's telling us the a value here is 1. And then the k value is the constant that's multiplying the x in the exponent there. So our k value here is negative 3. All right, so just getting a little practice working with these e functions, these natural exponential functions. And where we're going to go with this is we're going to introduce kind of the opposite of this function. And we're going to call that the natural log function. And we'll kind of get a little practice working with that. All right, so we'll see you then. Bye-bye.